And I got a few magnets, and they're not necessarily things that show well. Woo! There you go. There's a magnet. Behold, look, it's got red end and a blue end. If you look carefully, you can even see that the red end has an N on it. If it's got an N on it, what does that mean? Not negative. Oh my gosh, I'm just about to lose my mind. Yeah. North. And the blue end got an S on it, which means south. Yes, absolutely. Not neutral either. Okay. So many words. All right. So we got a magnet. Of course, here, I'll give you a chance to redeem yourself, okay? A North Pole always seeks out a what? A South Pole. I heard someone whisper it. Always seeks out a South. And a South Pole seeks out North. Yeah. So we talk about attraction. And this is that idea of, oh, no, don't worry. This is that idea that if even if it's not really true in dating, it is true in science, right? Opposites attract, for sure. All right, so naturally occurring magnetic fields that last for a long time, we call these ones, the source of these at least, we call them permanent magnets. Now the key word here is naturally, and I don't have a sample of this, but an example of it would be magnetite. Magnetite is an ore. It's an iron ore, and it's naturally magnetized. And there's all these people that have these apocryphal stories about how it was discovered. Maybe it was a shepherd walking in a field with a staff and put their staff down on the ground and picked up a rock that was attached to their staff. Ooh, the first discovery of magnetite. I mean, those kinds of stories are lost to history. We don't really know, right? So we can make up whatever story we want. But magnetite is a naturally occurring material. And the best I've got is, hey, look, there's a picture of magnetite. Doesn't it look like a rock? It is a rock, okay? So artificially induced magnetic fields that last a long time, well, those can also be permanent magnets. It's the last a long time part that we're focusing on here, but it's artificially produced. They're also permanent magnets. And an example might be, a horseshoe magnet. And I don't happen to have a horseshoe magnet on my desk, but I did show you the red-blue bar magnet, classic, right? I myself had a horseshoe magnet when I was a kid. I was probably always going to be a physics teacher, but my parents asked me what I wanted. I wanted a microscope and I wanted a horseshoe magnet. That was what I wanted for Christmas. And I got myself my horseshoe magnet. And of course, I went straight to work picking up iron filings in my sandbox. I went to the beach. Beach day. What does young me do? Bucket of sand, shovel, and my magnet. Gone to the beach, gonna have a great day. Came home, had a Ziploc bag. Filled up a Ziploc bag with iron filings from the local beach. Fantastic. Did little experiments with them and everything. And if you don't know what an iron filing is, you find iron filings everywhere. It's like I said, at the beach, you'll find them in the sand. But these guys here, this is a jar full of iron filings. Isn't it even just like, it looks like sand, right? Like if you get a good angle on it, can you see that? Like it's kind of granular in there. Yeah, maybe if I zoom out a little bit, refocus. Here, I got a jar of iron filings. See how it looks like sand? Yeah. Anyway, I got this other thing here. This is called a horseshoe magnet. I mean, it's not a horseshoe magnet. This is a cow magnet. Woo! And a cow magnet is a fun little device. It's just a permanent magnet like the one we're talking about right now, a bar magnet, but it's all rounded and smooth so that, cows and goats, they'll eat anything. Tacks, nails, shreds up their intestines, causes all kinds of problems. But these kinds of animals, they got 4 stomachs, right? And it turns out that a nice heavy magnet like this, if you feed it to one of those suckers, they'll eat it, but all the other junk that they eat will stick to it, and that'll keep it from tearing up their insides and causing infection in their intestines, like the sepsis. So this is a really kind of low-tech way of keeping your animals safe despite themselves, right? If you're in a farm situation where those kinds of pieces of sharp metal are going to be abundant, and then it just kind of sits there inert in their stomach, and hopefully the acid works away at the metal until it's all gone, right? And so if you can put a magnet inside of them, maybe you'll save them from themselves, right? So that's kind of a neat little thing. I suppose if there was a lot of metal they were eating, you might have to do stomach surgery. You have to depend on how important, or you have to decide how important that animal is to you. Uh, Maybe it's dinner, or maybe you're going to have to do stomach surgery because you really need the milk. Fair enough. Whatever you got to do. But I love that idea of the cow magnet. Artificially produced field properties that quickly fade. Well, these are electromagnets. And electromagnets, honestly, it's hard to just show you an electromagnet. This this is an electromagnet. If I zoom out, it's actually a bar magnet magnetizer. Somebody's covered up the the label at some point. Laser. This is super old timey, made in Chicago, Illinois. But it's a magnetizer. And what you're supposed to do is look. Somebody's even labeled it. You stick the north in on this side and the south in on this side. And so I've got two holes, kind of like a toaster. Stick the north in on this side. I grab myself another magnet, and I stick the south in on this side. And inside of those holes are two electromagnetic coils. They call them solenoids. And a solenoid really looks an awful lot like this is actually a spring, but it looks a lot like a spring. You run electricity in one end and it comes out the other end. And that electromagnet, this is what we're actually focusing on right now, will create a magnetic field inside of it and around it. And creating a magnetic field inside of and around an electromagnet means that if I put a piece of metal inside of it, the metal will become magnetized. And so this thing that looks kind of like a retro toaster, it's a retro magnetizer. And if we were doing a magnet unit for like elementary school kids or something where we were going to use a lot of bar magnets, and I wanted to make sure my bar magnets were really strong, over the course of a few days, maybe every hour or so, I would slip in a new set of bar magnets. And then over the course of a week, I'd have a fully remagnetized set of bar magnets, because what happens over time is bar magnets, even though we say that they're permanent, they can slowly lose their magnetization, right? So we want to like boost them up. So that's why a device like that might be invented, right? So electromagnets. So when I was a kid, we actually used to take iron nails. And I don't know if people do this anymore, but if you take a 9-volt battery, maybe I'll zoom back in again. If you take a 9-volt battery and you connect a wire wrapped around a nail, you're going to destroy your battery. You're going to run it dry, and it's actually going to warm up a fair bit. So you want to do it on top of, like something like a hot plate or something like that. Believe it or not, this was in a children's craft magazine that I got for Christmas. And I made this electromagnet when I was a kid. And you short circuit a 9-volt battery across a wire that's wrapped around a nail, and it does exactly what that little magnetizer toaster was that I showed you just now, but for like a fraction of the cost, right? And then you end up having a little magnetized nail. And then in the craft book, it told me to pick up iron filings, which is, of course, why I had to go collect them. And it told me that I needed to pick up staples, which, of course, it did. Like, nice little craft. So anybody could do this. Look, here's the apparatus diagram. Battery, nail, and then you take a wire and you wrap it around the nail and connect it back out to the battery. Really simple experiment, okay? Nice thing well, I wouldn't say I would give it to a kid, because there's a good chance you're going to overheat this thing, and there's a good chance that you're going to cause, depending on the electrolyte in your battery, the electrolyte to weep out and kind of get everywhere. And I have memories of having electrolyte on my hands as a kid. So, there you go. Crafts. Each their own, I suppose. Anyway, 4 magnetic facts. Any north-south pole combination is called a magnetic dipole. Now that's just a vocabulary thing. Next one is north and south can't exist alone. And I'll just say no monopoles. No magnetic monopoles, anyway. Of course, a charge monopole would just be a lone positive or a lone negative, but a magnetic monopole, that would mean that I have just a north and just a south. And really, like, if I take one of those bar magnets, like this guy here, I'm not going to chop it up, but you know that if I broke this bar magnet in half, wouldn't this blue end have its own north and its own south now? North over here, south over here. And the red end would also be north on this end, south on this end. It's not like the red side of this bar magnet is north and the blue side is south. It's actually telling you something about the orientation of the atoms inside. They're oriented like mini compasses. There are a billion trillion atoms inside this thing. Avogadro's number of atoms inside this thing, and they're all pointing that way. Weird. Not all of them. Some majority of them are pointing that way. It's more of a statistical thing that this thing is talking about. On average, more than half of them are pointing that way. It's not that this is north and this is south. That's something that kids maybe believe in or something like that, but we can't believe in that anymore, okay? So I'll take this guy away. There's no monopoles. I'm going to put a little block here. We already said this. Unlike poles attract. Like poles repel. I would say above that wiggly line is stuff that maybe you hadn't heard of before, and above, I suspect you have heard it before. I want to talk about what we mean by there being no monopoles and the fact that I could break that bar magnet in half and still have a north and south on both ends of each piece. But I want to get at it through this idea of domains. And domains, well, let's fill in the blanks first and let's make sure that the blanks all make sense. Okay, so domains or domain theory talks about microregions with net magnetic polarity orientations. And if I was going to take a look at my red-blue bar magnet, here it is, my red-blue bar magnet, okay? This is a schematic diagram of my red-blue bar magnet. Inside of this bar magnet, we think of having a whole bunch of little mini regions inside of it, almost like, little provinces within a country. Every one of those little provinces, those little domains, has its own orientation. In a country, each province, each state, whatever, is going to have its own political orientations. On the whole, each region might have its own orientation, but then we could say, oh, the whole country has its net political orientation, whatever that may be. And I'm not getting political about it. I'm just trying to make an analogy, right? When I talk about this actual bar magnet, this is a good model because I can think of there as being a whole bunch of different regions that kind of have micro orientations. But together I have a whole object that has its net orientation. Cool? In reality, this isn't the most nitty-gritty way of talking about it because there aren't really provinces inside of this. There aren't really boundaries inside of it. It's kind of an amorphous solid or something, right? But inside of this thing, there are like a lot of iron atoms. And each one of those iron atoms is its own individual compass. But that's just too much for our brains to handle. So we came up with domain theory. Does that make sense to people? It's a way to break it down, to chunk it out for ourselves, So when the domains are all unaligned in a magnetic material, the object produces no external magnetic field. In other words, if all these regions were, some up, some down, some left, some right, in equal proportions, they would all cancel each other out. That would be an unmagnetized thing. That's the domain theory way of talking about it. In the real world, with a billion trillion atoms, they're all kind of just random, is what we would say, right? No net, like kind of preferred directionality. Anyway, an external, oh, I'm going to use something new. An external B field, there, we'll do that for the first time. And a B field is a magnetic field. I can't remember the trivia on why we use B for magnetic field. You can look that one up, okay? I don't think it has to do with Latin. But anyway, an external magnetic field can help to line up the domains. And that's what I was talking about with my little toaster. You know, when I put a magnet inside of this little magnetic toaster, whoa, there it is. I'm putting this bar magnet into an external magnetic field, external to the bar magnet anyway, right? And so that bar magnet, in the presence of another field, is going to get magnetized. All the domains start to align. And so that's brings us to this next vocabulary word. It's called magnetic induction. And magnetic induction is, and I'm going to use the word inducing in the definition, inducing field alignment of domains using an external magnetic field. I'm going to say no touching required. So that magnetic field doesn't have to physically touch any more than when I stand on Earth and I feel gravity. The Earth doesn't have to touch me for me to feel gravity. The field has an impact on me. It stretches out through space. Action at a distance is the buzzword that people use, you know? Anyway, then there's this word inducing. And in electromagnetism, when we talk about inducing something to occur, something that I want you to hold in your mind is that inducing something to occur often involves causing to happen without touching. That's often an associated idea when we use the word inducing. So I just want to throw that out there as well. All right. Somebody asked me one time, could you make this into an illustration? Sure, why not? Here's a cartoon. North, south. And I'm going to label this powerful magnet. When powerful magnet is brought near to, here, these are a bunch of domains. Notice that my domains are chaotic. They're not all pointing in the same direction. When powerful magnet is brought near to not aligned I hate to say the whole world. Oh, you know what? I will. Ferromagnetic material. I'll use the proper word. Those of you that are chemistry people, they're like, oh, it must be iron-based. It is. We'll iron that one out later. Not aligned ferromagnetic material. The result ends up being, so here's my cartoony way of saying a result happens. I'll draw those two bars again, north, south. This is the original. The new one, the domains end up, they won't be perfectly aligned. But if I were to say on average, they kind of point in the same direction. You guys see what I'm saying? Not perfectly aligned, but we'll say that it's magnetized. So sometime later, magnetized material. And I'm not doing this little cartoon to be condescending or whatever. I think it's just nice to see like what we're talking about here, right? And it doesn't have to be a barn magnet being brought close to a ferromagnetic material. In fact, the source of the magnetic field could be anything. You know that Earth produces a magnetic field, right, around Earth. And as a result, iron bars are going to have domain alignments that line up with the Earth's magnetic field. Like each one of those little iron atoms inside of an iron bar is a mini compass. And just like any compass, it aligns itself with Earth's magnetic field. Now, if you take a piece of metal from, let's just say, like if you're doing archaeology, an Egyptian dig site, if you take a piece of metal and it's been sitting there for 2,000 years, its domains are going to align with the Earth's magnetic field. One way to check to see if somebody's tampered with a dig site is, has the metal come out of alignment with the field itself, with the Earth's magnetic field? That's a weird way to approach Egyptology, but this is something that we could think about. Yeah, the actual metal aligns with the Earth because each iron atom is its own magnet. Yep.
So is this why, like, when you have, like, say, like, metal on, like, a magnet, and then you take, like, that piece of metal off and touch it to another metal, that it acts pretty much like another magnet?
Yeah, exactly. That's exactly it. Actually, here I have a piece of metal here. This piece of metal was up against a fairly strong magnet for a while, and that exact same thing happened. If you take it actually is really easy if it's a small piece of metal. If you have a fairly strong magnet and you put a paper clip up against that magnet, the paper clip will become a little mini magnet. And then you can take that paper clip and pick up other paper clips. The problem is, like, look at this. All these domains, since I've been saying earlier, these domains actually are like clusters. It's actually just iron atoms, right? And we know what happens when you take an iron block and you heat it up. What happens to the molecules? They vibrate. And you can imagine that if I take this thing that's now aligned and I put it into a pot of boiling water, all these domains are going to shake, 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 shake. And by random motion, is the alignment going to be preserved or will it come out of alignment? It'll come out, right? So people say, well, what's the best way to demagnetize something? Of course, you have a magnetizer, but could you demagnetize it? Yeah, cook it, heat it up. It's going to come out of alignment. I mean, the domains will try to stay in alignment, but you keep on cooking that thing, you'll jiggle them out of alignment. Another way you could knock it out of alignment, smack it with a hammer. For real, if you mechanically smack this thing, drop it, you'll make the particles vibrate, they'll come out of alignment. So, I mean, like if you have a nice horseshoe magnet, maybe this holiday season, maybe you too are asking for a horseshoe magnet. And if you want this horseshoe magnet to last a long time, don't drop it. Don't cook it in a boiling pot of water. It'll last much longer. That's all, right? So like all this like kinetic molecular stuff from chemistry, also at play, right? So we haven't thrown that out the window. Yeah. If you froze it, I suppose if you wanted to, you could probably freeze your magnet and it might last longer, maybe slow down. But another thing, and superconductors want to be cool, but that's another issue. But this magnet, when I store it, you see those pieces of metal on the end? They're called keeper bars. And this is the keeper position. It turns out that when I put this here, the domains inside of that keeper bar align, sort of in a curve, but they align with the magnetic field of that bar magnet. And so like this is north. So this ends up being the north end of the keeper bar. This is the south end of the keeper bar. This ends up being the north end of the keeper bar. This is the south end of the keeper bar. And then I take my other magnet and I think, oh, I don't want these two magnets to do battle with each other. I want to go like this. Now the north end of this one's going to feed into the south end of this one. The north end of this one's going to feed into the south end of this one. And the domains actually are like reinforcing each other around in a loop. And I didn't invent this thing. This came, you can tell by the packaging, this came straight from the 1950s for your educational instruction. So now you've been instructed. Okay, people of the past, thank you. It even says to try me, and we have. All right, there you go. Made in England, Sheffield. Wow. Cool. I've learned a lot.